So today we're going to look at a topic called language modeling. And we're sort of going to start looking at sequential structures. And next week we're going to look at sequence-to-sequence models. And you can think of these models that, again, as probabilistic. To some extent, they are generative. And after next week, we're going to start going back to more advanced generative models like deep Bayes machines and variational autoencoders. But today what I'd like to do, and again, you should look at Hugo's class. I think that a lot of material that I'm going to talk about today is actually borrowed from his class. And the reason why I wanted to talk about sequential modeling as well as language modeling, because I think that it's a very commonly used area of research, and you know, so far we've been looking a lot at images, but today we're going to look at applications of neural networks to language. So we will, particularly in this particular class, we're going to focus on the text and natural language processing. And you can think of, much like what we've seen in the computer vision domain, we can design neural networks specifically for training specifically on the textual data. Now, one of the big issues for text is that text is very high dimensional. Right? If you think about representing words, we typically end up with vocabularies of size, 300,000. And that creates a few problems. Now, how do we represent the language, or how do we represent the textual data? So the first thing we're going to be doing is we're going to be mapping, we're going to be going from vocabulary of words to unique IDs. Right? That's the first step. Each word is going to be associated with a unique ID. And then depending on which criteria we're using, we can select which words are part of the vocabulary. Obviously, do you include misspelled words as the vocabulary? Do you include some derivatives or proper nouns and stuff like that? That's something that typically we'll have to decide on. For example, one thing we can do is we can pick most frequent words and ignore uninformative words, right? So, for example, words like the or potentially don't really help us that much. So typically these are called stop words. We can remove them, right? And for those, for international students, I know it's a big problem. Like I never myself can figure out where should I put the, where should I put right? And that's true for language. If you ignore these words, it doesn't really impact anything, right? And there is a lot of work also. How can you deal with out-of-vocabulary words, right? That's actually a big problem. Like when you try to do language modeling, you see something that you've never seen before, a new name or a new name of the restaurant or something new. What do you do? Right? And typically the easiest thing would be to map all of these words into out-of-vocabulary token, which is basically saying whenever you see a new word, it's just going to be assigned its unique ID, which is out-of-vocabulary ID. And if you look at the typical vocabulary sizes, in academia, you see sometimes 10,000 words, 250,000 words. If you're in industry, then you're going to be using, vocabulary of size millions of words. Now, here's how we can do the mapping. And I'm sure many of you kind of worked with language before. And I believe on your third homework assignment, you're going to look at simple models for language generation. And you'll deal with that problem. So let's see. Let's say we have a sentence, the cat and the dog play. And this is our vocabulary, right? The and cat, dot, and maybe out of vocabulary. And essentially, we're just going to be assigning, representing the sequence of words as a sequence of IDs, right? Sometimes, I guess, we're going to be denoting IDs with a symbol W. So we can think of this symbol W as a categorical feature for the original word, and we'll sometimes refer to W as a word, right? So W here would represent the words. And that's a common kind of representation. Anytime you see a sequence of words, you basically in computer, you would be representing it as a sequence of unique IDs. Okay? Given the vocabulary. So now, what we can do based on the word ID, we can get a basic representation of the word through one-hot encoding of the dictionary. So for example, if we have a vocabulary of size D, the one-hot vector for word ID 4 would be represented this way. Right? So every time, and later on, we're going to look at language models. We're going to look at, you've probably heard about word-to-vec embeddings and such. What actually is happening there is that every single word is represented in one hot vector representation, and you're learning its embedding. Okay? So, and one thing about one hot representation is that there is no assumption about word similarities, right? You're just basically constructing your vocabulary, and you're just assigning unique IDs to each word. You're not really, this representation doesn't really say anything about similarities between words. And this is natural representation to start with. In fact, we will be starting with this representation. It's a poor one, obviously, but that's the most commonly one we can use. Now, the major problem with one-hot representation is that it's very high dimensional, right? So the dimensionality of this embedding, dimensionality of this one-hot representation, E of W, is the size of the vocabulary. There's no way around it, right? So, for example, if a typical vocabulary size is 100,000, and you look at the window of 10 words, let's say you want to try to represent 10 words, you would basically correspond to an input vector of at least 1 million units, right? So that's not very good representation, and obviously if you start with this representation, you're going to be running onto overfitting. You have millions of inputs, you have millions of parameters to train, computation is going to be very expensive. So we have to do something different. Okay? So what we're going to do instead, and this is something that has been done, I guess, in the last 7-8 years or so, people, actually maybe more than that, actually, maybe 12 years, 13 years. Each word W is going to be associated with a real valued representation, C of W. Okay? So the idea is to really map words like the into some continuous vector. Right? Let's say in this case it's a 5-dimensional vector. So now you're going to be saying every single word is represented in a vector space. Okay? Now the big question is, how do you actually learn these representations? Right? But pretty much a lot of what you see today is the word embeddings. You've probably heard about word embeddings, and people are using it anytime you are trying to process either the sentences, you try to classify text, you try to generate text, or you try to find a sentiment in a document, or you try to do question answering, whatever that may be. Pretty much the state of the art today is to find these real valued embeddings of the words. And back in 2004, you can basically, you want to make sure that if you look at the word embeddings, the distances in the word embedding space, you want them to reflect some similarities, some meaningful similarities in the words, between the words, right? So for example, this is one particular representation where you're learning these embeddings, where you can see like all the counts are similar to each other, million and billion, semantically similar to each other. There's a bunch of points here that talk about different months. Their embeddings is similar to each other. So it's kind of finds, here you can find an interesting structure. So what we'd like to do is we'd like to learn a continuous representation of words. And we would like to use them as representations as input to the neural networks, right? So once we have this continuous representation of words, think of them as 50-dimensional vectors. Then we can use them for for the input into the networks. And what's important is that we can actually learn these representations by doing gradient descent. And we're kind of like constructing a third homework right now where you will do it yourself. So here it's interesting, right? Because you are effectively trying to learn what these representations should be, right? We don't only update the parameters of the neural network, but we're also going to be updating the representations of the input with a gradient descent step, right? So you're going to have some loss function, whatever that loss function you're trying to optimize. It could be classification loss, it could be predicting the next word, it could be predicting something else. Whatever that loss is, we're going to be designing algorithms so that when you take a gradient of this loss with respect to these embeddings, you can learn what these embeddings are, right? Now, let's look at the continuous representations. So C here is going to be a matrix whose rows are going to be representations of the continuous embeddings of words. Okay. So C is going to be of size whatever your vocabulary is by whatever the embedding space is. Typically, the embedding space is 50-dimensional. Some people use 100-dimensional. Some people use 300-dimensional, right? So depending how much data you have. And the way you can think about this, that in order to get the embedding of a particular word, you basically, it corresponds to the multiplication of one hot encoding by this matrix C. Remember, what is one hot encoding? One hot encoding is basically saying you which word you're looking at right now. And if you multiply it by matrix C, it's essentially picking up the row, the corresponding row in matrix C, right? Or view it differently, we're projecting the representations of the word that we're looking at onto the columns of C, right? So if I look at the word cat, the cat ID is 5. So, my one hot encoding is going to be 0, 0, 0, 0, 1, and then 0, 0, 0, 0. So if I multiply by matrix C, it's basically I'm pulling out the corresponding rows of C. And this is a continuous transformation, right? This multiplication here. And because it's a continuous transformation, what that means is that we can calculate gradients with respect to C. We can calculate gradients with respect to the continuous representation of the word. It's kind of like sometimes you can also think about it as taking the gradients of your loss with respect to the inputs, right? So you're changing what your input representation should be. And again, here your input representation is the continuous representation of the words. And in practice, you'd implement this particular representation through a lookup table, not with a multiplication, right? So you just create a lookup table, corresponds. This word corresponds to this embedding, this word corresponds to this embedding. And you're differentiating, you're taking gradient with respect to each embedding. So you can learn what that embedding should be. Any questions? We're going to look at some examples on that. So a language model is a probabilistic model that assigns probabilities to any sequence of words. Okay? So if I give you a sequence of words, I want to compute what's the probability of that sequence. And what you'd like to do is you'd like to basically assign high probability to sentences that make sense, correct sentences. And you want to assign low probabilities to incorrect ones. Right? Yes, question?
How do you train your word embeddings?
Yep, I'll get to that. Again, as I go back, the way you can think about training your word embedding is that you take the derivative of your loss, whatever the loss function might be, and different losses will correspond to different tasks. You just differentiate it with respect to the embeddings. Because the embeddings themselves are continuous vectors. So you can always take the derivatives with respect to the embeddings.
But you still need to get, so when you said that words like Tuesday and Monday were pretty close together, they obviously had a pretty, is it like an unsupervised reconstruction that you do?
Yeah, let me get to that. I'll come back to that. It's a good question. Maybe let's look at the language model and we'll come back to how do we actually train the embeddings. Okay, now, so here's the task of the language modeling is really to assign high probability to correct sentences, the well-formed sentences, and assign low probability to not well-formed sentences. And this particular model plays a crucial role in speech recognition, machine translation systems. Because in a speech recognition system, if the speech recognition system forms a sentence that doesn't make much sense, so because words are not quite right, the language model can fix it up. Like if my speech recognition sentence say, I go to my class, like twice, I say, I go to my class, then the language model will say, that's not a very probable sentence. Because typically I don't say go twice. But if I only say one time, I go to my class, then this sentence will have very high probability. So my speech recognition system, even though it predicts something different, the language model can correct and can really give me the right output. So in many cases, these kinds of language models, machine translation is the same way. You translate it into, let's say, from English to French, and you use a language model to assign the probability and maybe do a few changes to the sentence so that whatever the sentence you end up with will have high probability under your language model, right? So this plays an important role in a lot of different application areas, speech recognition and machine translation in particular. Because sometimes you look at the machine translation, it translates you and you give, outputs a sentence, you look at the sentence and say, whoa, this is just like grammatically very wrong sentence. It just doesn't make much sense, right? So that means you have a very poor language model. So for example, here's an example, une personne intelligente. So here's your translation. A person smart, right? If you go word by word, that would be the naive translation. But in English language, a person smart will have very small probability because people just don't say it that way. A smart person would have a very high probability. So the output of the translation system would be this, even though word-to-word translation would be this, right? So let's look at how we train this thing. So an assumption that's frequently made is the nth order Markov assumption, right? So you're basically breaking down the problem into a sequence of conditional probability estimations where you're saying you're going to be looking at the conditional probability of predicting the next word given n minus one previous words context. So typically the context would be of size 5 or 6. So given 6 previous words, you're trying to predict the probability of the next word, right? So in this case, the tth word here is generated based on only n minus 1 previous words. And we will refer to this as the context, right? So we try to predict the word at time t. Is going to depend on the word at t minus 1, t minus 2, all the way up to t minus n minus 1, right? So the context of size n minus 1. So this is what we're going to be optimizing, okay? Does that make sense? So if you have a sentence, you say, I'm going to be breaking it down into the probability of the first word times the probability of the second word given the first word times the probability of the third word given the 2 previous words and so forth. And then you just shutting it down at the context. So you're only predicting the next word given a fixed context. And that's a hyperparameter that you have to decide on your own how big of a context you want to look at. So here is the model that basically was proposed back in 2003. And let's look at that particular model. This is called neural language model. So I guess it's been 15 years since people started looking at, or even more than that. I think in the 80s people were thinking about these ideas. So let's say you have an index for word t minus 1, okay? The index, think of it as one of k encoding scheme, right? What you do for this index, you're projecting it to the continuous representation. Let's say this is 20-dimensional or 50-dimensional. And you do the same thing for the previous words. Then you taking the average, you pass it through 10H nonlinearity. It could be sigmoid, it could be ReLU, or it could be just linear. There are multiple variations. But here we're passing it through 10H nonlinearity. You get some representation. So what is this representation? This is a representation of the overall context, right? What you've seen so far. And then based on this representation, the 10H representation, then you have a softmax. You have a softmax of predicting the next word. So it's almost like a classification problem where, you know, if your vocabulary is of size, let's say 10,000, then you're solving 10,000 word classification problem, right? Because you're effectively trying to predict what is the probability of the next word, right? So now if you look at the overall system is just a classification neural network. Takes the previous context, finds the embeddings of the words, takes the weighted average, push it through nonlinearity, and then solve the classification problem of predicting the next word. So one of the interesting thing about this model is that you're basically learning representations that can generalize to previously unseen context, right? So if you look at standard language models that were very popular, you look at the Ngram language model. What is the Ngram language model? You know, bigrams, very, very popular. Bigrams is basically just count in your training corpus how many times the word cat is followed by the word dog, right? Or how many times the word cat is followed by, I don't know, cute, like cute cat, right? And let's say you're like counting how many times you see that, right? Well, if you see that a lot, then that means that it's highly probable. If you don't see this at all, you basically say it's improbable, right? But here, what happens here is that by learning these embeddings, if I give you the context that you've never seen before, you can still, this model can still take this into account, right? Because you have the embedding of this particular word, you have embedding of this particular word, and then that neural network can figure out how to take this information into account. So these models are much more powerful because it allows you to transfer to n grams, right? N previous words that you're seeing, not observed in the training corpus. Okay? Now the question comes, how do you learn the embeddings? See here. Right? How would you learn the embeddings? At the training time, you know what the correct prediction should be, right? You know the correct word that you should be predicting out of, let's say, 10,000 possible words. So you're solving 10,000 way classification problems. So you know what the correct word should be. You just plug this correct word, you use cross entropy, and you differentiate cross entropy loss with respect to these parameters and respect to these parameters, which are the parameters of a standard neural network. But then you're also differentiating with respect to these vectors. And you say, change the representation of these vectors so that I can accurately predict the correct class, right? So it's actually very simple, right? You're basically just learning, taking derivatives with respect to these continuous vectors and just updating. So it's almost like intuitively, these indices don't change because, you know, this is one of k-encoding scheme of which word you're seeing. But you can take derivatives with respect to these vectors and effectively learn what the correct input to the neural network should be, right? Because it will change these embeddings in such a way that I can accurately predict the correct class. Yes?
So does those dotted lines mean skip connections?
Yeah, so in this case, they basically said, you know what, we can share these parameters, right? It's a lookup table, effectively. It's just a representation of the words. And these dotted lines were representing skip connections. So you can go directly from, you know, you just basically look at these representations and you have a linear layer into the softmax. So you don't have to go through nonlinearity, you just build a linear system. Just given the context, take a linear layer which effectively just summarizes the context and predicts the next word. So if you look at this particular model, it's a two-layer neural network, right? The first layer is just the embeddings of the words. The second layer is just the 10H layer that aggregates context and then predicts the next word. So by doing gradient descent and by doing standard learning, you can actually learn the parameters of this model And you can also learn the embeddings, right? So that's one way of doing it. Now, obviously, there are multiple. After this, there were a whole bunch of different papers that basically say, you know what? I don't want to predict the next word. What I want to do is I want to predict surrounding words, right? And that's effectively what the word-to-vec representation does. Word-to-vec representation basically says, pick this word, push it through, the embedding, and try to predict this word and this word. So try to predict surrounding words. There's been another work that basically says, take a bunch of words and predict the word in the middle. And I'll show you some more examples of like generalizing it to sentences or paragraphs and so forth. So it's all about forming the problem. It's unsupervised because you don't really need supervision here. You're just basically saying, do you predict the next word given the previous words? Because for language modeling, it's very important. If you want to learn better embeddings, maybe you just like take the word and predict surrounding words. Predict context around your particular word. So now, as I mentioned before, you can potentially generalize context not seen in the training set. So for example, what's the probability of the word eating given the context the cat is? Right? It's pretty probable. The cat is, it could be playing, could be eating, it could be jumping and such. But let's say you have the 4-gram model and you have the cat is eating is not in the training corpus, but the dog is eating is at the training corpus. Okay? So you're seeing dog is eating, but you've never seen the cat is eating. And then you basically, through training procedure, you kind of learning that the representation of the word cat and the dog are similar because they appear in similar contexts, right? They appear in similar, like the context is about similar. So then the neural net will be able to generalize to the case of the cat, right? And it will say the cat is eating as a high probability. And that precisely this particular setting is what makes these models to some extent work better than standard n-gram models and such. Even though n-gram models with like very special smoothing techniques and they work fairly well. So we know how to propagate gradients of a network with respect to the parameters, right? We know how to compute the gradient of the linear activation function of the hidden layers. Let's see. Let's look at, and let's note that the submatrix connecting WT are the hidden layers of W. So here you can basically say, this is W1, this is W2, this is Wn minus 1, like looking at the context of size n minus 1. And the gradient with respect to these continuous vectors, with respect to the embeddings, is just taking the derivative of the loss function with respect to these lookup tables, right? And that comes down to just taking the derivative of whatever the pre-activation is times Wi. And this is just a fancy way of writing. You're only updating it for the word that appears at time t minus I, right? So you're updating these vector for the word context or the representation of the word W, right? Yes?
The labels in the training data, they wouldn't be unique, right? Because the last word in a string, it might be two different words with different probabilities. How do we train for that?
Sorry, the last...
the label is the last word in a string of words.
So there's no particular label. You're always trying to predict the next word given the previous words.
But there might be two different words for a string.
Sure. Let's say you have a sentence, the cat is, and one sentence says playing, another sentence says jumping. So what do you do in this case?
There would be different probabilities of both of them.
Yeah, so what basically at the training time, you pick the first sentence, and you say the cat is, like in this sentence you see playing. So you just basically say, well, my target is playing, take the gradient, update the parameters. Next time you're seeing the cat is jumping. So you clamp the jumping, which is the correct target, and you backpropagate. What the model will learn, the model will actually learn eventually if these two sentences appear like about the same time, number of times, the optimal solution for the model would be to predict 0.5 probability of playing, 0.5 probability of jumping, right? And that's essentially what the model is going to be doing. Because the cat can be playing, could be jumping, could be eating, could be like, there's like out of 100,000 possible answers, maybe there are 10 probable ones. And that's exactly what the language model will try to do. It's not going to tell you that the cat is red, right? Like this is something that you don't see at the training corpus, and hopefully the probability of this is going to be very small, right? So you don't try to kind of like compute the, you basically say, here's the sentence. All I'm trying to do is predict the next word given the previous words. I know what the correct prediction is, trying to predict it. Obviously, for these kinds of problems, given the same context, you can have multiple different alternative targets, but the model will calibrate itself, right? Yes?
I'm just curious to know how big the data set for training should be in order to get significant results, and also how the data set is formed. Like, would be that
Yeah, it's a very good question. So how big the data sets are to learn this thing? It's actually kind of funny because this work was done back in 2003, and I think they've used like PenTree which is what you're going to be doing for your homework, I believe, to train this model or version of this model. And you look at the embeddings and they kind of look okay, but nothing significant. Like it basically kind of wasn't like you see some, like I've shown, like June, July get grouped together, and like, but it wasn't like you see and you say, wow, this is really semantically very meaningful. So people kind of ignored it, and then basically like a few years later, with the rise of GPUs and data sets, if you train this model on very large corpus, it works surprisingly well. You get very meaningful features, you get very meaningful embeddings, you kind of start seeing similarities, and that's when people revisited these kinds of models, 5-6 years ago. So, ultimately, the nice thing about these kinds of models, and then obviously with the rise of speech recognition technology, people are spending a lot of time figuring out how to build these language models. Because speech recognition under noisy environments, you can't quite get the exact, perfect speech recognition. But in many cases, the language model can correct, sometimes improperly, but it does have a correction. It's kind of, I remember at University of Toronto, there was a faculty professor, and his name was Radu Crow. So if you ask Google Phone or Siri or any other, like, who is Radu Crow? And the model would say, well, who is Russell Crowe, right? So obviously the language model kicks in because it basically can't really identify exactly the names, but in the language modeling part, who is Russell Crowe is actually pretty commonly used. So it basically corrects itself and thinks that you're asking about Russell Crowe, not this Professor Radu Crow, right? But now, you need basically lots of data, but at the same time, you don't need any labeled data, right, to train these models. Yes?
So does this mean that you, for every word of t-1 to t-n+1, you save an embedding for that subset?
So yes, so the way to think about this is that you always keep the embedding matrix C. C is of size, whatever your vocabulary size is, times dimensionality of the embedding space. So typically, if you see 10,000 or 100,000, so you always keep the matrix of 10,000 by 50 in your memory, right? And then when you see this context, you just pull the relevant elements from this matrix, right, which is the lookup, and you're just updating these representations based on your loss or based on what you're trying to optimize.
No, I mean, like, intuitively, I'm not getting as in, if the word is the cat is and the dog is, would these two combinations of words have different meaning in the embedding spaces?
Yeah, absolutely, because this is going to be the dog is, or the cat is. This embedding of the cat and the dog, they might be similar, close to each other, but they're not going to be exactly the same. So this representation will be different for the dog is or the cat is, but they're going to be very similar to each other. If I say the dog is versus I am going, like these two representations are going to be very different from each other, right? I'll show you some examples later on. It's all about how similar these embeddings are, because they're supposed to capture some similarity between the words. But again, you're not a priori telling the system that dog and cat are similar. Maybe if my task is to really classify, is this a dog sentence or is it a cat sentence? Maybe I want to learn the embeddings of these two words to be very different from each other. A lot of it depends on the task that you're trying to solve, right?
You need to do the normalization for the matrix, because when you say the similarity, I see you are using the Euclidean distance. They are not in the same scale.
Yeah, so here you're not really using, if I go back to here, all I'm trying to do is I'm trying to solve this thing. I don't really care about similarity of the words or Euclidean distance between the words or anything like that. All I'm trying to do in this particular context is I'm trying to say, find me these embeddings, whatever they might be, such that I can correctly predict the next word given the previous words. The similarity piece comes out naturally because, you know, just like in this context, the cat is eating, the dog is eating, they kind of, if they mean the same thing, you have the same predictions. Yes?
Is there ever a problem where the words that should be similar might find different local minima when they're...
Yep, they might be.
It's like when you're initializing, would you initialize using random?
Yeah. You initialize, whenever you're training these models, you would typically initialize them to be some Gaussian with some random noise. And typically you start off training these models, they're very, you know, all the vectors are very close to each other. And as you're training, the vectors will separate depending on, again, the task that you're trying to solve. So let me show you a couple of examples. So how do we evaluate? So in language modeling, common evaluation matrix is perplexity. And what is the perplexity? It's simply the exponential of the average negative log likelihood. So we have log likelihood. We take the average of the log likelihood. We take the negative and then we exponentiate. And the reason why you do exponentiation is because sometimes the log likelihoods are typically, you know, very small numbers, right? Because the probability is less than 1, and so if you're taking the log, it's typically something fairly small, so it's very hard to see the differences, what the differences are. We decided, why don't we expand, and so the differences will look bigger. Yeah, so this is an evaluation on particular corpus where you have n-gram model, neural net, and neural net plus n-gram. So you can see that it's much better, lower is better. And so it's doing, you know, you can combine neural networks with n-gram models, and these typically work quite well. Any questions about this? Yes?
What has never appeared in the corpus, the embedding with the embedding point?
Yeah, so if the word has never been in your corpus, and let's say it's not in your vocabulary, then you just assign it the token unknown. So any words that you haven't seen, you just assign it to unknown. And you just learn one embedding representation for unknown. It's not optimal. It's not the best thing to do. But this is the common thing to do, particularly for language modeling. If you have a vocabulary, and at the training time, you've never observed that particular word, like let's say you have in your vocabulary cat, but your training corpus doesn't contain cats. Test corpus contains a cat, then there isn't much you can do because the embedding of the word cat is just going to be whatever the random initialization you've assigned to it, right? And so there is no kind of like, that's why training, like, you know, if you look at word-to-vec representation, I think they've trained on the entire Wikipedia. And so you have embeddings of the word like proper nouns, right? You have the wording of the embedding of the word Obama, right? And kind of like closer to the word president. Like you have embedding of the words like Mark and Julia, right? So it's like the embedding of a name. So you can basically embed anything you want. Yes?
So if one particular word has two very different meanings.
Yeah, so if one word has two very different meanings, then you kind of screwed, basically. There are some extensions to these models where you have different embeddings depending on the context. So there is some word, like the word bank, for example. Like could be river bank, could be financial bank, right? And so in many cases, what people are doing, people are not also relying just the embedding of single words, but people start relying on the embedding of the whole context. Like if I say the river bank versus the financial bank, both of them will have very different representations. So there is some work in that space. Okay, so how about, let me just show you a couple of examples for the rest of the class. How about generating sentences? So here's an example of given an image. You can imagine an image that you extract some features from the image using convolutional neural nets, let's say, and then you're generating a sentence, right? So can you do that? And here's what we'd like to do. We'd like to basically say, well, given this sentence, we want to really say probability of the first word. What's the probability of the second word given the first word? So how do we figure out what the probability of the first word is? We just basically estimate it from the training corpus. Like how many times the word a appears in the beginning of the sentence? Probably a lot. How many times the word the appears in the beginning of the sentence? Probably a lot. How many times this full stop appears at the training sample? At the beginning of the sentence, just a full stop. Probably almost zero, right? You never have a sentence with just one full stop. And so forth. And then you're just building these conditional models. And this is what you can do, which is kind of interesting, right? If you have enough examples, kind of like going from images to text, you can do that. And it's very simple. You can basically, this was done using neural language model. You have image features, you condition on these image features, and you just build a simple neural language model. Like predict the first word, predict the second word, and so forth, conditional on the image features as well. So image features are like biases into the hidden layer of a simple neural language model. Can create these things. And then create these things, which is kind of funny. Like the two birds are trying to be seen in the water, right? Or the handlebars are trying to ride a bike rack, which is pretty good, right? Or a woman and a boat field, right? Like the top one. Which is pretty good. I mean, if you kind of, squint your eyes a little bit, you'll probably see a giraffe there, right? So, okay, so now how do we deal with, how do we make our predictions be more efficient? So there's been a lot of work trying to say, well, what I try to do, I guess here, you're basically saying the dog have B and cat have B. And so, okay, so let's say you're trying to basically, example, the dog and the cat. And you're trying to predict the dog and you're trying to predict the cat, let's say, right? That's the sentence that you're trying to predict. What you can do is you can say, well, you can build a hierarchical softmax, which kind of allows you to speed up prediction. Because what's the problem with the softmax? The problem with the softmax is that if I have a vocabulary of size 2 million, then it's like I'm solving 2 million way classification problem, right? Like I have to predict, like given this context, what's the probability of the word red? What's the probability of the word July? What's the probability of the word Obama occurring after I see the dog and the, right? And such. So, if I have vocabulary, very large vocabulary, it's very computationally very expensive. But what you can do is you can build a hierarchical output, or you can build a hierarchical softmax. So here you're basically saying, what I'm going to do is I'm going to build a tree. This is my vocabulary, and I'm going to build a tree. And what I'm going to do is I'm just going to traverse down the tree. I'm going to say, well, the probability of the cat is going to be, what's the probability of the left branch? Because I want to predict the cat. I'm going to say, what's the probability of the left branch? And it says just sigmoid. And then I can say, what's the probability of the right branch? And then what's the probability of the right branch? Right? So the probability of the word cat is going to be this probability times this probability times this probability. Right? So I have basically, instead of looking at the softmax of 1, 2, 3, 4, 5, 6, 7, 8, I'm basically only looking at the path down the tree. So you basically have logarithmic reduction in computational cost, right? And people have also used this particular idea for classifying images when your output classification is not, 100, but your output is like 20,000 classes. You're trying to predict 20,000 classes. You can also build this hierarchical structure that allows you to do it in logarithmic space, in logarithmic time, right? Yes.
So is this counted as a graphical model?
It's what?
Is this kind of like a graphical model?
It's not, yeah, you can think of it as a graphical model, but it really is just a tree-structured output. You're just basically building a tree. And to go down the tree, you're basically saying, well, it's the probability of this. And you're just training at each branch of the tree. You're basically saying, well, given this context, conditional in the context, this branch has higher probability than this one. And this branch has higher probability than this one. And this branch has higher probability than this one. So you basically know what the targets are. You can train. And you can also train these splits for these probabilities. Yes?
Is the tree structure here just for computational reasons like the software
Yeah,
code?
that's right. It's just the computational reasons. Yeah.
It doesn't have any semantic?
No. It's just the computation. Yeah. Yeah.
Is the tree randomly constructed?
Yeah, it's a good question. So how do you construct a tree? That's one of the big problems, because ultimately what you'd like to do is you'd like to construct a tree so that the dog and the cat, they live in the same subspace. Because if dog is here and the cat is here, then it becomes very problematic, because similar context, you're now confused, like do you go here, do you go there? So that's an unsolved problem. What typically people do is people construct randomly tree, they train the model, and then they recluster the words, and they reconstruct the tree, and then train the model and reconstruct the tree. So there's like iterative process. So it's not very clean process, because constructing the trees is difficult. Like you can start with a random tree. Sometimes people use WordNet or some kind of semantic similarity to construct the tree and then just adjust it. Yeah, and so in this case, for example, if I say what's the probability of the cat, it really is 1 minus sigmoid times sigmoid times sigmoid, right? Because the sigmoid is always probability of going to the right. 1 minus sigmoid is probability of going to the left. So you can kind of speed things up quite substantially. So you can use, like I said, you can use randomly generated trees, you can use linguistic resources like a WordNet, you can learn the hierarchy using some kind of recursive partitioning. And again, this is done, you train the model, you somehow refit the tree. You train the model, you refit the tree. And then there is kind of, it was a paper back in 2008 in Jeff's group, Hinton's group, and they reported the speed up of about 100 times without performance decrease. So they've shown for very large scale models, this hierarchical softmax can really give you leverage in terms of speeding up the output. Okay, in the last sort of 20 minutes, in the next class we're going to look at recurrent networks, but what I'd like to do is I'd like to also tell you some of the ideas behind RNNs. So far we've looked at neural language models. And what is a neural language model? Neural language model just takes at the context, some k-dimensional context, just aggregates and predicts the next word. Right? Recurrent neural networks take it to the next level. What you do is you're basically saying, well, there's some 1 of k encoding scheme, you find some representation of the word, and then you have this recurrent structure. So the previous representation affects the next representation, right? And now you can basically kind of, if your sentence contains, 20 words, you kind of go from left to right. So the difference is that the previous hidden state affects the next hidden state. Whereas in neural language model, just the context affects the hidden state. Once you've lost this context, there is no relationship between hidden states. So what is a recurrent neural network? Well, you have the hidden state at previous time step. You have the input at time step t. And you basically have a nonlinearity, phi. Typically it's 10H or sigmoid nonlinearity. And you can also view it as a deep neural network with tied weights, right? Because the input to hidden weights are the same and hidden to hidden weights are the same. One thing that I wanted to point out is that there are different versions of these models. There's something that's called LSTM, long-term, short-term memory networks, GRU, gated recurrent units, just different flavors of these RNN style models. Some of them work better than others. One thing that you can do, just wanted to show you that in some cases you can replace this summation with element-wise multiplication. Or you can add element-wise multiplication plus summation. And in many cases that actually helps you, much better in terms of modeling sequential structure, in terms of predicting probability of the next word given the previous words and so forth. There's been also some language models that actually predict characters, like what's the next character given the previous character, or the previous sequence of characters. LSTMs, so what these models are, it looks like a scary figure over there. But LSTMs themselves, they're a very simple sort of extension of RNNs. In fact, I guess they were published by Schmidhuber and Hochreiter in 1997. But at that time, it was way too complicated for people to kind of train. But at the same time, the LSTMs are actually very simple. They're very elegant models, but they're very simple. Let me just actually look at, let's see. Okay, let me start from here. So this is something that's called input gate. So what is the input gate? Well, you take your observation at time t, you take your hidden state at time t minus 1, and then there is something that's called a cell state, a cell unit. So you have one additional cell unit at time t minus 1, okay? So we have input, we have previous hidden state, and we have a previous cell state, okay? Plus the bias. We pass it through the sigmoid, so this is going to be number between 0 and 1, okay? Then there is something that's called forget gate, and I'll tell you where we're using them. Again, it's exactly the same structure. You take your current input, you take hidden state at t minus 1, previous hidden state, you take the cell state, the previous cell state, you take the sum, you pass it through the sigmoid, so f is also number between 0 and 1. Okay? Now, let's look at the cell state. What is the cell state? Cell state is basically saying the way I'm dating the cell state is I take the cell state at t minus 1, and I take what would be the input to the RNN, which is the hidden ht minus 1. This would be my RNN model, right? Now, what I'm going to do is I'm going to take the weighted average of the cell state at previous time step plus this nonlinearity. So this is kind of like saying, what's the previous hidden state, what's my input is. Now, why do I need these f and I? The role of f is to say, well, this is a number between 0 and 1. If this number is close to 0, then I'm just going to forget this, right? And my cell state is effectively going to be essentially what the RNN is doing. If my f is close to 1, then I'm going to keep the previous cell state. This is called input gate. It's also a number between 0 and 1. If it's 1, then I really care about my current input in the previous hidden state. If this I is 0 or close to 0, it basically says ignore the input. Because think of it, right? If I set I of t to 0, the only update to the cell state is just the previous cell state. It's like I'm ignoring what the input is. So that's why this is sometimes called input gate, which basically modulates how important your input is. And F is the forget gate, which is essentially telling you how important your cell state is, right? And then you basically take the OT is the output gate. Again, it's the same, modulates how important to output something. And you basically compute the 10H of the cell state, right? So the reason why we need the cell state is the only reason the difference between LSTMs and standard RNNs, and it's a big difference, is that this relationship is linear, right? The previous cell depends on the next cell state. So when I differentiate this ST with respect to this one, this relationship is linear. One of the big problems with RNNs is that when you differentiate sigmoid, you always have things like sigmoid 1 minus sigmoid. which is a number much smaller than 1, typically. And so you forget very quickly what happened in the short term. This guy doesn't have this problem because it's just the linear. Let's say ft is 1. If it's 1, then the gradient is always going to be 1. So it's always good to have some kind of linear component in your RNN. And that's essentially what LSTMs are doing. And all the different flavors of GRUs, all they're effectively doing is they're just tying these things together, saying, well, inputs gate and forget gate should be like, this should be alpha, this should be 1 minus alpha. Why do I need this? And maybe I'm always going to be setting my output gate to be 1 because I always want to output something. So I can drastically reduce the number of parameters. But the key component is really this linearity component. So the next cell state depends on the previous cell state in a linear fashion. Right? If I put sigmoid over this thing, then that's it. That would cause the problems because when I have to differentiate, your gradients are going to be shrinking towards 0. Right? So in some sense, at the high level, LSTMs are pretty simple. You basically say, well, my cell state, my hidden state, really, is the previous hidden state plus some nonlinearity based on my input. And my output is really just the nonlinear output. So this is a linear part, this is a nonlinear part. Any questions? And all these other equations like input gate, forget gate, output gate, these are all just simple numbers that are gating. How important is the input? How important is the cell state? How important to have the output and so forth. So they don't really contribute that much to, they do, but this was the significant piece that makes LSTMs work much better than standard RNNs. Yes, question?
Is this similar to like residual networks where you introduce?
Nah, not quite. You don't have any skip connections here, right?
So you're propagating like information from CT-1 to CT in a linear way.
Sure. So the other thing that people have looked as people have looked at sort of bidirectional RNNs, and the idea is that the way to encode a sentence, for example, is you go forward in time and you go backward in time, right? So there's one chain that's forward, one chain that's backward, and then you just concatenate these states. And the reason why you want to do it is because if you look at the middle one, this unit will incorporate some future. This unit will incorporate some past. And so when you concatenate, you kind of like get the representation of some context around your word, for example. Any questions? So for example, one thing you can do is you can say, well, and we're going to look at sequence-to-sequence learning next class, but here's just a preview. Let's say I have some input sentence, and what I'm going to do is I'm going to try to predict some output sentence. Or given some input sequence, I want to predict some output sequence. It can be a sentence, like given a sentence, predict the next sentence. It could be a video sequence. Given a video sequence, predict the future video sequence. Or it could be a language, given in English, predict French. Or, so the use cases are, there's a lot of different use cases where you have some sequence, you're trying to map it to some other sequence. And this is the representation of the input sequence. And people have kind of looked at a whole bunch of different representations, right? So you can say, well, one-to-many, many-to-one, many-to-many, many-to-many in different ways. So how do you exactly construct these things? So you always have sequences. You're trying to map one sequence to another sequence, right? So obviously that's important when you're trying to do activity recognition in videos, when you're trying to model language, trying to model speech, whatever that might be. Here's one model called skip-top model, which is given 3 sentences, sequential sentences, a tuple of sentences. You want to have an encoding of sentence SI using LSTM, but the sentence SI is attempting to reconstruct the previous sentence and reconstruct the next sentence. Or you can think of it as like predicting the next sentence or predicting the previous sentence, both. So you try to predict the context around the sentence. So for example, if you have an input sample like I got back home, I could see the cat on the steps, this was strange. Like that's actually one passage from the book. So I'm encoding this sentence. And from this sentence, I'm trying to predict I got back from home, this was strange. right? And so how does it work? Well, you generate the previous sentence, you generate the forward sentence, and you're learning the representation of the sentence. It's like trying to learn representation of the sentence to vec. Given the whole sentence, you're trying to represent it in a vector form. So what's the learning objective? Well, the learning objective is just the sum of the log probability for the next and the previous sentence, conditioned on the encoded representation. So this is forward sentence, this is the previous sentence. It's like a language model. Given the embedding of the sentence, you're just trying to predict conditional probability of words in the next sentence and conditional probability of words in the previous sentence, right? And the whole thing is differentiable, right? It's just one LSTM. You have two other LSTMs, and you're just backpropagating through the whole thing, which is pretty straightforward. To do. So here's some results. If you train this model on 74 million sentences, about million unique words, and you train it on 11,000 books, here's what you can do. So based on the representation of the sentences, I can take this sentence. He ran his sentence inside his code, double checking that the unopened letter was still there, and you look for nearby sentences among 500,000 randomly selected sentences. This is the closest sentence. He slipped his hand between his coat and his shirt while folded copies lay in brown envelope, right? So if you look at these two sentences, they kind of, they're not exactly the same, but semantically you would argue that they're somewhat similar, right? Or you can do, like these are some other examples. I know, I'm sure you'll have a glamorous evening, she said, giving an exaggerated wink. I'm really glad you came to the party tonight, he said, turning to her, right? So you can see that this is just the retrieval of sentences. In many cases, it actually works pretty well. Let me show you some examples. There is one particular task that people really care about in language communities, is this notion of semantic relatedness, which is, I give you two sentences, and you have to tell me, are they the same or not? Do they semantically mean the same thing or not? Right? And obviously, that can be used for paraphrasing, that can be used for sentiment analysis, for a lot of different things. If you can tell me these two sentences mean the same thing, so this is a particular data set, you kind of judging them 5 means that they're the same, 1 means they're completely random sentences. So here you can use this representation, you can embed the representation of the sentences, you have vector representation of the sentences, and then you can just basically compute simple statistics like looking at the distance or looking at either cosine distance or some features between the two sentences, and you build a simple classifier. And you can actually do quite well. So in 2014, these are basically a lot of different submissions. These are results reported by a lot of different kind of different algorithms. What's interesting is that these models and the variations of it, they basically were achieving state of the art, right? Which is interesting because these models were not trained. These models were trained basically in unsupervised fashion. There is no linguistic knowledge. There is nothing about language at all. You're just basically looking at the prediction task. So it's like just sequences of words, IDs, and you're basically learning the whole thing from scratch. And it's interestingly that you can actually outperform a lot of semantic evaluation submissions. A lot of these semantic evaluation tasks, people were using linguistic knowledge, right? Like what's connected to what, doing a whole bunch of things. Whereas if you pretty much have a simple model just trained on very large corpus, it can, work really well, which is kind of was surprising to us. A little bit depressing, but surprising. Here's an example of, hold on, do I have an example of, this is just an example from the paper. Look at this example. A man is driving a car. The car is being driven by the man, right? If you look at the third one. The model predicts, the ground truth is 5, the model predicts 4.9. So the model basically says these two sentences, they're the same, they mean the same thing, right? The man is driving a car is being driven by the man. Or, there is no man driving the car, a man is driving the car. Then the prediction is like 3.5, which basically means that they're not the same, but there is some similarity. They're not completely random sentences. One would correspond to completely random sentences. Here's an example where the model is failing. A person is performing tricks on a motorcycle. The performer is tricking a person on a motorcycle. Right? So this is, the model says they mean the same thing, but they don't really mean the same thing. Right? Or, yeah, so this is one particular, this is an example where the model is really failing. But if you look at the top one, the person is performing acrobatics on a motorcycle. The person is performing tricks on a motorcycle. So the model says these two things mean the same thing. So this is Microsoft Research MSR paraphrase corpus. And again, this model does very well. Just skipping through that. And then if you kind of like look at some of like movie review sentiment, you look at the customer product review, subjectivity, objectivity classification, opinion polarity, and so forth. These models kind of pretty much, again, very much on par with, close to the state of the art, right? So just a little bit more training, perhaps, you could get very good representation. And again, here you're not fine-tuning to the word embeddings. You're just basically saying, here's the representation of my sentence. How well can I do in terms of classifying, how well can I do in terms of the sentiment analysis? And also these are unsupervised, whereas a whole bunch of things that use supervised sort of algorithm for fine-tuning the embeddings. Okay, so, and just a little bit of summary. This is also an interesting space, and in next class we're going to look at extensions of these models. So, people haven't looked at the deep encoders, decoders, large context windows, encoding, decoding paragraphs. You can also embed the paragraph. You can embed a whole bunch of things. Yeah, potentially you can do way, way better. If you look at the code and the data, it's also available online. So you're more than welcome. If you're interested in like getting sentences and doing something with sentences, you can just do sentence embeddings using this particular algorithm. In many cases, they work fairly well. All right, so next class we're going to look at sequence-to-sequence models, and next class the second homework is due, and your project proposals, one-page project proposals are due as well. And then I'll give you a little bit of a break.